Welcome back, everyone. So continuing where we left off in the Chapter 8 lecture note outline during the last lesson, we are going today to look at the energy levels that we learned about with the orbitals. So we learned the placement of the orbitals in terms of lowest energy ones to higher energy ones. Today we're going to actually extend that a bit, and we're going to be looking at how to link that up with the elements on the periodic table. So the purpose of today's lesson is we're going to go through the periodic table and see where an element is placed, how that relates to its electronic configuration, and also start to see a little bit about how this theory, this quantum mechanics theory, kind of lines up with our Mendeleev's periodic table. And we're going to see some kind of interesting things with that. Also learn how to start sort of seeing the connection between things we know, like the charge state for different elements, and how that relates back to the configuration of electrons that it has. So let's get started with that. So during the last lesson, I showed you the relative energy levels for the various orbitals up till, I think, around 6s, maybe 6f. Look at the periodic table, though. Notice that there are 7 rows of elements. Now, we want to be able to describe where the electrons are in all of these elements. And it turns out we're going to need to take into account the fact that we have these 7 rows. Now, I showed you a little trick when you're coming up with the relative energy for the different orbitals. And I showed you a grid kind of like this. I'm just going to recreate that here. Now, this grid, if we know how to use it properly and how to write it properly, shows us the filling, the expected filling or the predicted filling for the different orbitals, whether it's a 4f or a 6s or whatnot. And this is kind of a diagram showing, if you're drawing these green arrows that I'm showing here, which orbital follows which in terms of their predicted energies. Now, we're going to actually go ahead and today we're going to learn how to use the periodic table as a better way of actually looking at this and figuring out where the electrons are around an element. So while this grid is handy in terms of figuring out which orbital follows which, I'm going to actually show you on the periodic table how the structure of the periodic table is actually lined up with this knowledge that we already have about the orbitals and their energies. So to understand how this works, the first thing we're going to need to learn are some principles as far as how electrons are filled into the orbitals when we sort of fill them up to look at where they are around an atom. And the first thing I want to show you is something called the Aufbau principle. Now, when we're thinking about where electrons are going to go first when we put them into orbitals around an atom, it would make a lot of sense if we imagine these electrons having the lowest possible energy that they could have in any given situation, right? This makes a lot of sense. Things generally move to their lowest energy state, right? Like if you take a ball and you just kind of let it fall, right? It's going to fall to its lowest energy level. It's not going to float up or go straight up into the air, right? It falls down because of the force of gravity. And electrons are in a similar situation. Well, it's not gravity, it's their energy in terms of electromagnetic radiation. They're going to actually have their lowest energy state at any given time unless they're excited to a higher energy state. So what the Aufbau principle is it's a principle that takes that into account. The word Aufbau is a German word which means building upwards from the bottom to the top. And basically what this principle states is kind of what I was just saying, is that when you have an electron, it will populate the lowest available energy orbitals first before moving them into higher energy orbitals. So if we're thinking about an atom and we're assuming that atom is in a ground state or the lowest possible state it can be in, we're going to put electrons or assume electrons around that atom are going to be in the lower energy orbitals before they're in the higher energy orbitals. Because if they were in the higher energy orbitals, they would just fall down to the lower ones. So it makes sense then that electrons should be in lower energy states when we're thinking about the ground state for an electron. So I'm going to sort of diagram this principle here. On the left, I have a an orbital filling diagram where I'm only showing the 1s and the 2s orbitals, and then I have this line pointing upwards to represent increasing energy moving in this direction. And we know that the 1s orbitals are lower in energy than the 2s orbitals because the 1s has a lower principal quantum number, or is closer to the nucleus than the 2s orbital. Now, if we had one electron to place in around this, say like in a hydrogen atom, it would make sense that that electron would occupy the 1s orbital first before the 2s orbital, because that is the lower energy orbital. So this would be the correct configuration for the situation where there was one electron available. So this is generally following this Aufbau principle. So this is a good electronic sort of idea or configuration, sort of the idea of what the electron would be doing in this situation. So the electron's going to occupy the lowest available energy possible. This is the Aufbau principle. Now, what would be an example of something that wasn't good, didn't look correct? Well, if we draw an electronic configuration where we have these same orbitals available and we have a one electron system, if for some reason we put that one electron in the higher energy orbital, that wouldn't be following the Aufbau principle, simply because it's in a higher energy orbital. It should be in the lower energy orbital. Now, this might be the case for an excited state atom, but typically we're talking about, and I would have to specify that, we're usually talking about ground state atoms when they're not excited by an input of energy or something. So let's move on to another principle. That's the first principle. It's called the Aufbau principle. There's another principle that we have actually already kind of seen a little bit. It's called the Pauli exclusion principle. Now, what the Pauli exclusion principle states is that electrons, we've already learned that they have this something called a spin, a magnetic spin. And we've learned that they're quantized in terms of this spin. So electrons generally only have two spins available, right? It's spin up or spin down. There's nothing in between. Well, the Pauli exclusion principle is a principle that states that if an electron is in an orbital, it can't be with another electron that has the same spin. Another way of saying that is that electrons within the same orbital must have opposite spins. Okay, so you can have an electron with an opposite spin in the same orbital, but not with the same spin. So given that we only have two spins available, what does that mean about how many electrons can actually be in the same orbital? Let's take a look. So let's first think about if we had just one electron around an atom. Now that electron can have an upspin or a downspin, and that's fine, right? And it doesn't really matter which one we're thinking about. The spin isn't going to matter much for us. So both of these are fine situations to write. We have a 1s electron in an upspin or a 1s electron in a downspin. Now let's take a look at when we have two electrons. Now if we have two electrons, remember, we have to have them in opposite spins. So if we had an upspin and a downspin in a 1s orbital, that's fine. Or if we have a downspin and an upspin and they're just drawn the opposite way, that's fine also. Both of these are fine situations because the electrons have an opposite spin. Let's compare this with a situation that would not work, right? Let's say that in a 1s orbital we had two electrons that both had an upspin. This would not be good because the spins must be opposite. Furthermore, if we had two electrons that were both downspin, this is also bad. Okay, so what this means effectively is that we can have a maximum of two electrons in a given orbital if they must have opposite spins, which is what the Pauli exclusion principle states. So in pictures, it would look like this. If we tried to put 3 electrons in a 1s orbital, that wouldn't work because one of them would have to have the same spin as another one. That's because electrons, again, have a quantized spin. So as a consequence of that, there is a maximum of 2 electrons per orbital. This is known as the Pauli exclusion principle. Now we're going to learn about another principle here called the Hund's rule. Hund's rule is a bit like the game Monopoly when you're building houses. You have to build them evenly. You can't put 3 houses on one space and then none on another. It's the same with electrons. If we are placing electrons into different orbitals that are of the same energy, we have to spread them out evenly before we start pairing them. So the first example I have here with 3 unpaired electrons in 2 p orbitals is good, but the second one here is bad because we haven't filled up that last orbital before we started pairing them. So we've got to fill evenly before we pair them. So here are a few more examples of that, like this third example that I have drawn here. This is fine, right? Because we have filled all 3 orbitals, 1, 2, 3 first, and then we pair after that. So the 4th electron has to be paired, but before we pair it, we have to fill these orbitals singly first. Okay, and then here's another example. It's fine to have these all paired. It's just that before we do that, we're going to see the electrons spreading out into that orbital before we spin pair them. And that's the reason for that is there is a little bit of an energy cost associated with putting an electron into the same orbital as another one. Even if they have opposite spins, it's a little bit of an energy cost. Because you can think of it like you're fitting 2 things into the same space. It's just a little more squeezed in than if they're spread out first. Okay, so that's a good analogy to think of when you're doing it. So we've got good, 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 and this is bad. And that's Hund's rule. So now that we've seen the electronic configuration principles, these 3 principles, what we're going to do is we're going to look at different elements on the periodic table, and we're going to use these principles to try to come up with a picture or a notation for what the electrons are doing, what state they're in around an atom. If we know how many electrons there are and we have these principles to follow, it turns out we can come up with a pretty decent picture for what the electrons are doing around that atom. So let's go to the next page and take a look at that. So before we actually go on to the next page in the notes, what I would like you to do is print out a copy of the periodic table or have this available. I want to show you a few features on it that we're going to use when we go forward. This is going to help you kind of understand and figure out what the configurations of electrons are around atoms. So print that out and let's take a look at it. So one really interesting thing about the periodic table that we have, and remember the periodic table as we've talked about, was originally organized in the one we have now anyhow by this guy Mendeleev in the 1800s. Now Mendeleev didn't know, they didn't have knowledge about protons or electrons at that point. And Mendeleev's periodic table was organized solely based on the properties of the elements. So, and its basically organization has remained unchanged since then. Now, interesting thing, fast forward to, the 1900s, and quantum mechanics is developed, and they learn about a lot of the things that I've shown you here with the different orbitals, where we have the theory about s orbitals and p orbitals and d orbitals and f orbitals and all of these different principles I just showed you. Now, it turns out that these 2 very kind of separately developed things, the periodic table and quantum mechanics, actually turn out to sync up, match up really well on the periodic table itself. And that's kind of what I want to show you right now. So the first thing that I want to show you is the rows on the periodic table. So we have these different rows, and I want to label them for you, starting at 1 and then going all the way down to 7 along the left. So we have 1, 2, 3, 4, 5, 6, and 7. Now these are the rows on the periodic table, and we're going to make the connection between these rows and that principal quantum number n we had. So for example, if we're talking about the elements helium and hydrogen, those are in row 1, where if we only had n is equal to 1, that's the principal quantum number, the only orbitals available at n is equal to 1 is the s orbital, right? Which, remember, the s orbital holds a maximum of 2 electrons. And I want you to notice something here is that in this n is equal to 1, there are 2 elements, right? Just hydrogen and helium. And the s orbital can hold 2 electrons. Now let's look at hydrogen for a minute. Hydrogen has 1 proton. And that means if it's neutral, it has 1 electron. And that would be if we had 1 electron in the 1s orbital. Now if we look at helium, helium has 2 protons. And if it's neutral, it can have 2 electrons. And that would fill up the s orbital. We're going to look at that as a feature, something that we can see actually on the periodic table. Now let's look at a few others real quick. So let's look at n is equal to 2. right? Now remember at n is equal to 2, when we have that principal quantum number 2, there are 2 subshells, right? We get the S subshell and the P subshell. And notice here that we have 2 elements that are in this area over here, where we could have 2 electrons. So if we're talking about lithium, then we have a total of 3 protons and 3 electrons, or we have a total of 4 protons and 4 electrons. The difference between these is just 1 electron. And then we go over here and we see 1, 2, 3, 4, 5, 6. Okay, 6 elements over here. So we can think about this as being S elements on this side and then P elements on this side. And we actually call them this. We call this the S block, and this is called the P block. Let's take a look at that in more detail. So thinking about s orbitals, right? S orbitals, like 1s or 2s or 3s or 4s and so on, no matter what n it's in, it can hold a maximum of 2 electrons, right? So if we think about this group over here, the group 1 and group 2, it is 2 elements wide, right? It's got 2 columns in it. And this means that this takes into account the 2 types of s electrons that we can have, right? They could be a 1s1 or 1s2 or 2s1 or 2s2, etc. So this is called the S block, and it consists of 2 elements wide. Okay. Now helium is kind of an interesting thing. It fits in over here. We keep it over in group 8 because it behaves like a noble gas. Now what about p orbitals? P orbitals, as you remember, there's a px, a py, and a pz. So there are 3 orbitals total in that subshell, right? And there's 2 electrons in each one, which means that we can have 6 total electrons. Notice that the P block has 6 elements across it, going from boron over to neon or aluminum over to argon. The P block is 6 elements wide. And if we add 1 electron for each element, this makes a lot of sense. So the P block matches up with the theory about quantum mechanics. Now, what about these d orbitals, right? The d orbitals, there are 5 of them, right? And there's 2 electrons because of Pauli exclusion principle in each d orbital. That means there are 10 total electrons. And guess what? The d block that I've highlighted over here has 10 elements in it. So if we go from scandium over to zinc, we're talking about incrementing through 10 electrons there. Now, what about these elements down here in the F area, the F block as they're called? Well, there are 7 F orbitals, which means if there are 2 maximum in each one, in each F orbital, that's 14 electrons. And guess what? The F block has 14 elements going across it. So this is very interesting, right? If the elements are organized according to their properties, they match up with the predicted theory about quantum mechanics. Now, this chart that I'm showing here is a graphic that you can download on Canvas. It's called an orbital filling diagram for the periodic table. And basically what it is it's kind of a cheat sheet to the periodic table and also where the orbitals line up. So it shows the S block, the P block, the D block, and the F block. And if you kind of read it from left to right and from top to bottom, it also shows you the organization as far as the energy levels going from lowest to highest. So we see up here in the top left that if we started with hydrogen over here, this is the 1s or the lowest energy orbital. And then if we go to the next the next line, we get to the 1s, right, which is the next, we put another electron in that 1s. And then we go to the next line down here, which is 2s, and we have 2 electrons that we can put into the 2s orbital. After we fill up that 2s orbital, we then continue forward and we go to 2p. So if we look at this, it goes from 1s to 2s to 2p, and then after 2p, we fill that up, and right, that takes 6 electrons, 1, 2, 3, 4, 5, 6. We then go to the next line, and we see the next was 3s, which takes 2 electrons. And then after 3s, we go over to 3p and fill that up, and then we go to the next line, and we go to 4s. Now, one thing you might remember from the energy filling order that we saw earlier is that after 4s, it doesn't go to 4p like you might expect. it actually goes to 3D first, which is shown here. So the first element here, scandium, is in the 3D column, the first 3D. And we fill up that whole D block first before we go to 4p. So that's kind of the usefulness of the periodic table, one of them anyway, there's many, but it shows you how the different elements have different electronic configurations based on where they're placed. Now, just a few things to note that you can actually get from this diagram, which again, you can print out off of Canvas. And you can use this on your exams as well. That the letter N for the D block is always one number behind that of the S block that comes before it. So for example, if you look at 3D, which is here, the S before it is 4S, right? Also, for the F block, the N is 2 behind, it's 2 lower than the S block before it. So the element cerium here, which is located in between this element and this element, 58 is here, 57 is here. It's 4F here, which is 2 lower than 6S. And this 5F is 2 lower than 7S. You can also think of it as being 1 behind the D block in front of it. And the filling for those orbitals is shown here below, where it goes, first it goes from 6S to 4F, and then from 4F to 5D, and to 6P, 7S, 5F, and 6D, and so on. So that's the basic idea here. Now we're going to look next at looking at specific elements and, like, say, pinpointing an element out here and saying, where are its electrons? And we're going to see that they fill up from the lowest to the highest, right, following the different principles that we have, like the Aufbau principle, Pauli exclusion principle, and Hund's rule. And with that, we can come up with a pretty good picture about where the electrons are. And then it turns out we can use that picture to explain a lot of the things about the chemistry about those elements. So let's go take a look at how that works. So what we're going to do first is look at a nitrogen atom. This first example here says a neutral nitrogen atom, and it says it has 7 electrons. We'll talk about why that is here in a minute, just to revisit it. But basically what we're going to do is we're going to look at a neutral nitrogen, and we're going to write out a configuration of the different orbitals that that nitrogen has, figure out what those are, and then figure out what electrons are in what orbital, using the principles that we have. So we have the Aufbau principle, we've got Hund's rule, and we've got the Pauli exclusion principle. And then after we do that sort of graphical representation, we're going to learn about the shorthand notation, how we can write it out just in like a short little line, just to write out a notation for it. And all the while, feel free, please have your periodic table and possibly this orbital filling diagram so you can follow along and it makes more sense to you that way. So let's get started talking about nitrogen. So as it says here, a neutral nitrogen atom has 7 electrons. Now, why is that the case? Well, if you look at nitrogen on the periodic table, you'll see that it has 7 protons. Now, from that information, we can definitely say that if it's neutral, it also must have 7 electrons. Now, what we're going to do is we're going to populate the orbitals that are available for nitrogen with the electrons. And I've drawn a schematic here showing that nitrogen has the 1s orbitals, the 2s orbitals, and the 2p orbitals. Now, why? Why doesn't it have d orbitals or f orbitals? Well, that's because nitrogen is in the second row, right? So if we kind of look at where nitrogen is over here on the periodic table, you'll see that it is in n is equal to 2, right? So I'll write that over here. N is equal to 2 for this row. Now, if n is in n is equal to 2, right, what types of subshells are available at n is equal to 2? Well, n is equal to 2 has 2 subshells. It has the s subshell and the p subshell only. So that's where we get the s orbital, and we get the 2s, of course, because that's also available, and then the 2p orbitals. So we have s and p orbitals available to us at n is equal to 2. Okay, so at n is equal to 1, we only have the 1s orbital. And then at n is equal to 2, we get the 2s orbital. And then we get the 2p orbitals, and there's 3 of them. Now what we're going to do is, those are the empty orbitals. Now we're going to put these 7 electrons into those orbitals. And the first rule we're going to follow is we're going to fill from the lowest energy to the highest energy. So the first electron of those 7 that we put in goes into this lowest energy orbital, the 1s orbital, okay, right down here. That's the lowest energy one. We're following Aufbau principle of doing that. Now that's only 1 electron. We have 6 more. Where does the next one go? Does the next one go in the lower energy orbital or the higher energy orbital? Well, that's right. It has to go into the lower energy orbital here. Now, the only problem is that this orbital already has an upspin electron. So how do we draw in this second electron? Well, that's right. It has to be an opposite spin or spin down. So let's go ahead and draw that. Okay, so that's 2 electrons. Now we have to get the third one in there. Now, where does the third one go? It can't go into this 1s orbital, which happens to be lower in energy because it's full, right? It has an upspin and a downspin. We can't put a third electron in there and still have it be an opposite spin. So that means we now need to go to the next lowest energy orbital, which you'll see is the 2s orbital. Okay, so we have to go to the 2s orbital. Notice also that what we've done so far is we've put 2 electrons into the 1s orbital. On this filling diagram, we've done this. We've filled up this spot and this spot. And then the next thing we go to is this third spot here, which is the first electron of the 2s block. Okay, so we're going to go here and we're going to put an electron in. It doesn't matter if I draw it upspin or downspin. I usually just draw upspin first, but feel free to draw downspin if that's what you want to do. Okay, so there's our third electron. Now we're going to need to put a fourth one in. Where does that electron go? Well, it's the same as before, right? We're not going to start filling up this 2p orbital system before we fill up this lower energy one. We just need to make sure that the next electron we put in here has a downspin or the opposite spin of whatever electron I've already drawn. Okay, so there's my fourth electron. So we have 4 electrons. What element would that be if we only had 4 electrons? Well, that would get me up to beryllium, right? Which notice is over here in the s block. It's the end of the s block, right? And that would be right here on this. So the end of the s block. Now, we're going to make a jump to the p block over here, right? Which is boron. That's over here. So the next electron we put in, which is the 5th electron, gets us to boron, which is right over here. And we can put that in any of these spots. It doesn't matter which one because they're all the same energy. I usually just go from left to right, however, and then I default to my upspin electron. So let's go ahead and draw that one in. Okay, so I've got my first electron in the 2p block. Okay, so we've got 5 electrons now, and we're going to have to get up to 7, right? So we have 2 more electrons to put in. Now, am I going to put that next electron in with this electron? No, that's because remember that Hund's rule says that we have to spread out our electrons evenly into orbitals of the same energy before we pair them up, because there's a cost to pairing up electrons. So the next electrons we're going to put in will go here, and then the next one will go here. And it doesn't matter what spins I draw because they are not paired, so I can arbitrarily pick. Again, I usually just default to upspin, so I'm going to go ahead and draw those now. Okay, so if we take a look at what we've done, we have 7 total electrons drawn in this configuration. We've got 2, 2, and then 3. So that's a total of 7. So this would be the correct electronic configuration for nitrogen. And I'm just going to write down here something that we call the shorthand notation, which writes it out as a sentence. Notice here I have 1s2, 2s2, and 2p3. These numbers here represent the shell for each electron. Then we have the letters of the subshell, and then up above, kind of as exponents, I have the number of electrons in each of those shell-subshell combinations. This is called the shorthand notation. Okay, so that's our electronic configuration for nitrogen. What we're going to do next is look at an orbital filling diagram for an iron atom. So you might want to actually see if you can come up with this one yourself. I'm going to do it here now, but go ahead and give it a shot if you think you can come up with this. Okay, so the first thing we're going to do is we're going to figure out how many electrons this neutral iron is going to have. Okay. So if you notice here, iron is element 26. That means iron has 26 protons. And if it's neutral, that means it will also have 26 electrons. So now that we know how many electrons neutral iron is going to have, let's actually look at where it's located on this orbital filling diagram. And let's come up with a list going from lowest energy to highest energy of the orbitals that iron will be expected to have. Notice that iron is the sixth element inside of the 3D row, right? So it's in the D block, it's the sixth element in. Let's write out all the orbitals that we need according to their energies leading up to that. So we'll start off with the 1s orbital, right? And then we go to the 2s orbital, and then we go to the 2p orbital in the p block. And there are 3 of those. So let's draw those out. Okay, after that we get 3s, so there's going to be 1 of those. And then we go over to 3p. And again, there are 3 of those, right? px, py, and pz in the 3p area. Then we go to 4s, okay? And then how many d orbitals are there? 5. There are 5 d orbitals. So let's draw all 5. That's in the 3d block, okay? Now I'm going to fill these up from bottom to top, filling with 26 electrons. And I'm going to follow all the rules I've done so far. So we get 2 in 1s, 2 in 2s, and then we're going to fill up the P block. And I'm just showing sequentially. It's like first we show them all in the same spread out following Hund's rule. And then we're going to pair them up following Pauli exclusion principle. And then we go to 3s. We pair those. We're going to fill up 3p. And notice what I'm doing here is I'm just going up to the D block, and I'm going to have how many electrons in that 3D block? 6, right? Because to get to the 6th space in the D block, I have 6 electrons. So I'm going to spread those out in the D block one at a time. So I get 1, 2, 3, 4, 5, and then the 6th one is going to be paired, and that's iron. So let's write out the shorthand configuration for this, or the notation. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Okay, and that's iron. Okay, so that's how we do this, basically. It's pretty straightforward as long as we can keep those, which order the orbitals are in, and we have those 3 principles in hand. Now, there are some cases where you will look up an electronic configuration on, say, on the internet. Like, there are some elements that I can name. I'm not going to name them now, but I could put out an element name, and if you look it up on the internet, you will get a different configuration than what you would come up with using the method that I've shown here. And that has to do with some fairly sophisticated experimental reasons that have to do with the way that these metals behave, certain special exceptions. Now, I don't want you to learn any of those exceptions. I want you to follow this method. And I would like you to be able to get the electronic configurations using this chart and the method I've shown you without knowledge of those exceptions. So if I wrote down an element, say some element over here in the periodic table that had a configuration that you looked up and it was different than the configuration that I would predict, that would be incorrect. I want you to follow this. So please don't look these up on the internet to get the configurations. I would like you to come up with it on your own using this chart. Okay, so that's all I have to say about that. Let's go to the next page and try a few more of these out. So let's try this next example, and in this example, we're gonna try neon. So it says, draw the orbital filling diagram for neon in its ground state. We'll always usually be doing these in the ground state. What do you notice about neon in the ground state? So we're going to have to come up with a picture here and go through the same process I just went through. So figure out how many protons are in neutral neon and how many electrons are in neutral neon, and then figure out what orbitals are present, and then fill them up with electrons. After you do that, go ahead and write out the shorthand notation and see if you get the same result that I have as I show here. So neon is element 10, and it has 10 protons, and if it's neutral, it's going to have 10 electrons. Also, it's in the second row. It's a second row element. So that means it is n is equal to 2, and it will have the s orbitals and the p orbitals available to it. So let's draw those out. Okay, now I'm just going to go ahead and fill these up with the 10 electrons. So there's the 6, and then we get up to 10 that way. Notice here that it's completely full, right? There are no empty spaces available, so we couldn't put any electrons in, and all of the electrons also are paired up, okay? So they all have pairs. We're going to keep that in mind as we move forward. Let's write out the shorthand notation for this. It's 1s2, 2s2, and 2p6. Some things to note. We call this electron that I've drawn here, this orbital, these are called the core or the innermost electrons. And the higher energy ones that are on the outside are called the valence electrons or the valence shell electrons. These are the outside electrons. They're higher in energy. And we're going to keep that in mind also. It's a terminology that we're going to find very helpful. So these are our core electrons at the lower energy, and then these are our valence electrons. In general, if we have the highest N, that would be the valence shell with the highest principal quantum number around an atom. Okay, notice that neon has 8 electrons in the valence shell. Okay, also notice that neon is in group 8 on the periodic table. That's something that we're going to see is a definite trend. The group number often will tell us the number of valence electrons around an atom. Okay, so if you got that right, great job. Let's go to the next page. We're going to look at dealing with an ion now. Instead of just a neutral atom, we're going to look at a charged atom, an ion. So let's go take a look at the next page where we're going to look at the nitride ion. So in this example, we're going to draw the same orbital filling diagram for, this time, a nitride ion in the ground state. And then I want you to see if you notice anything in particular about this electronic configuration when you're done. Okay, so the first thing that you are going to need to do is figure out how many electrons does this nitride ion actually have. So what is a nitride ion? Well, it's a nitrogen that has a charge, and you might remember that nitride, if you look at the periodic table, or you might just remember this, nitride is nitrogen with a negative charge, specifically with a 3 negative charge. Okay, now we can figure out how many electrons a nitride ion has by thinking about the number of protons and the number of electrons. So a neutral nitrogen, not a nitride ion, but a neutral nitrogen has 7 protons, right? That's because it's atomic number 7, okay? A nitride anion will have the same number of protons, right? It's still a nitride, but it will have a different number of electrons. So if neutral nitrogen has 7 protons and 7 electrons, what does a nitride anion have? Well, that's right. It must have 3 more electrons than a neutral nitrogen to give it that 3 negative, right? And that means we're going to have 10 electrons around it. So we have 7 protons and 10 electrons, and that gives us a 3 negative charge. This is what a nitride anion is. Now notice here that a nitride anion has the same number of electrons as neon, right? The noble gas that it is closest to in the same row. So neon and nitride have exactly the same number of electrons. Well, shouldn't that mean that they also have exactly the same electronic configuration? Well, let's take a look. So if we write out the electronic configuration of the orbitals, we find that we're also in row 2. So we have the 1s and the 2s and the 3 2p orbitals available. Now let's start filling these up with electrons. So I'm going to fill from lowest to highest, and then I'm going to pair the 1s and the 2s electrons. And then once we get here, let's pause here for a second. Notice that this is the configuration for a neutral nitrogen, right? 7 electrons. Now let's draw next to it the nitride anion and just look at the two and how they're different. We have the same type of orbitals, like 1s and 2s, and then we have our 3 2p orbitals. But now we're just talking about 3 additional electrons. Now where are those 3 electrons going to go? They're going to go into the p orbitals that are currently unfilled. So there, there, and there. So notice here that this is exactly the same diagram that we had for neon, right? Exactly the same. So what we actually often do is show this abbreviated with brackets around the noble gas that we are comparing with. It turns out that electrons around an atom will often seek out what we call a noble gas configuration because all of the electrons are paired in a noble gas configuration. So we often see noble gas configurations commonly. So it's helpful to come up with an abbreviation for them. And this is how we do it. So the shorthand notation would be bracket neon, and then that is the same as writing 1s2, 2s2, and 2p6. This is called the shorthand, or the noble gas shorthand for an element. And we can use that. So let's take a look actually at the next page. We're going to actually look at the relationship of different groups on the periodic table and kind of summarize a lot of this information and see if there's some shortcuts we can glean by looking at the periodic table. So let's go take a look. So it turns out, as we're going through all of this, that this information about valence electrons and core electrons, as well as noble gas configurations, is going to be really helpful when we go on to understand how chemical reactions take place and how bonding takes place in molecular compounds. So we already kind of know this a little bit, but chemical reactions involve electrons, and specifically they involve the sharing and or transfer of electrons between different atoms. And it turns out that the electrons that are involved in those chemical reactions are the ones that are the highest energy, not the lowest energy ones. And we've learned to call those high energy electrons valence electrons. And it's going to be really nice for us to see on the periodic table that the group number and the position of an element on the periodic table tells us how many and the situation that the valence electrons are actually in. And from that information, we can often predict how chemical reactions will proceed. It also follows that the lower energy electrons that we're calling core electrons are not involved in chemical reactions. And there's some good reasons for that, mainly the fact that they are paired. So really what we're going to see is that looking at the electronic configuration tells us which electrons will be participating in reactions and which ones won't, and maybe why that is. So let's actually summarize this information in a table that I have here below. So in this table, what we have is a list of some elements, just some samples. And then we're going to write out the configurations, just the electronic configurations, like 1s2, 2s2, etc. And then we're going to summarize those. We're going to shorten them to the noble gas shorthand that we just learned how to write. And then we're going to write down also, we're going to keep track of the number of valence electrons that are in these atoms. So we'll look at a bunch of different examples, see those valence electrons, how many they have, and then we're also just going to compare that with the group number for the element. So let's go ahead and start this with hydrogen. So hydrogen, simplest element, it's located over here in the S block, and it has 1s1 as a configuration. We don't have a noble gas shorthand for it. It has one valence electron, and it's in group 1. Now what about helium? Helium is in group 2, and it has 2 valence electrons with the configuration 1s2. We give it the noble gas configuration, bracket helium. Okay, now let's go take a look at lithium. Now lithium is in the second row, right over here. And you'll notice it has 3 protons. Neutral lithium would also have 3 electrons. So while in the second row, where n is equal to 2, also has p orbitals, we're not going to be filling up any of the p orbitals because we only have 3 electrons. So the configuration we get is 1s2, right? That gets us from hydrogen, it gets us helium. And then we go down to the second row, and we get lithium, which is the first electron in 2s. Okay, so we get 1s2, 2s1. The noble gas configuration for this, if you notice, has helium at its core. So I'm actually going to move the periodic table over here for a minute so we can take a look at what the significance of that is. So notice that lithium right here follows helium, right? So lithium at its core has a helium configuration underneath its valence shell, just like the noble gas shorthand shows. And this is true really for any element. So like for instance, if we were looking at selenium down here, selenium, if we go sort of backwards all the way through the P block and the D block, back here we get to potassium. Right before potassium, we see argon. At its core, selenium has an argon noble gas at its center. And all of the valence electrons are just tacked onto that noble gas core. So we're going to look at that kind of for the rest of the elements that we have. When we write out the noble gas shorthand, we're going to recognize what noble gas is at the core. And those are fundamentally the inert cores for all of these elements. So let's finish our table here. So we have one valence electron, and that's group 1 for lithium. Let's look at nitrogen. Nitrogen is over in group 5, and it should have 5 valence electrons. And you'll notice its configuration shows that. So we see that after helium, we have nitrogen showing up group 2s2 and then 2p3, which gives it 5 valence electrons in group number 5. Fluorine, a few atoms down, is in group 7 of the periodic table and should have 7 valence electrons, which it does. Its core electrons are helium, followed by 2s2, 2p5, so that's 7 valence electrons in group number 7 for fluorine. Now let's take a look at neon. Neon is the next noble gas down, and that's when we add an electron to fluorine, and we get the noble gas shorthand is just bracket neon, and that's in group 8, and it has 8 valence electrons. Phosphorus, same group as nitrogen, just one more row down. So it has basically the same valence shell configuration, just a different noble gas core. So the core noble gas of phosphorus is neon rather than helium for nitrogen. So if you compare those two, they just have a different noble gas core, but the same number of valence electrons, which is 5 for both. And that makes a lot of sense, right? That's kind of the whole point of the groups of the periodic table. It's based on their chemical properties, which in fact is based on the electrons that are in their outermost shell. It's sort of their interface to the world are these valence electrons. Okay, now we get down to the next noble gas, which is argon, and that has a full shell in the same row as phosphorus. So the 3p shell is full, and that's bracketed argon. That's the noble gas shorthand for it. It's in group 8 and has 8 valence electrons. Now let's look at a metal. Let's look at strontium next. So notice strontium is in group 2, and it's located down here right next to rubidium. So we're in group 2. Now let's try to just make a guess ahead of time what its valence shell will look like. Well, it's going to have an electron in this this row, which if we count down, we're talking about this is row 1 here, 2, 3, 4, and 5. So the valence shell will be in row 5 for strontium, and we'll have 2 electrons in that. So the valence should be a 5, and it's in the s block, so it should be 5s2, which is where strontium is. Now, what's the noble gas for strontium? Well, let's take a look over here on the periodic table and see what noble gas actually shows up before strontium. So if we go backwards, right, this is 5s2, 5s1, and then we go back over to krypton, which is back here. That's the row up. That would be the noble gas at the core of strontium. So strontium has all this stuff leading up to krypton below it. So let's write out the noble gas configuration here for strontium. So once we get through here, this means we're finished with neon, right? Neon has this configuration 1s2, 2s2, 2p6. Let's go, that's row 2 that we've completed. Now we're gonna go to row 3, or n is equal to 3. So we get 3s2, and then we go to the p block with 3p6, and then we're gonna go back down to the 4th row, and it's 4s2. Then we have the d block, and we have 10 electrons in the d block. Then we have to finish out the 4th shell, which is 4p6, before we go to the 5th row, which is going to have 2 electrons in it. And again, that's the noble gas core of that is krypton with 5s2 in the valence shell. And strontium is in group 2 and has 2 valence electrons. So that's basically how this works. And we're going to, basically the take-home thing for this is we want to look at the group number and understand that tells us something about the configuration of the electrons that interface with the environment around the atom. And it's possible from that we can predict some of the chemical properties that we will see from different atoms. So before we wrap up, let's just briefly mention some of the important points from this. First point is that the group number is equal to the number of valence electrons. Okay, now that's true for the elements that we usually deal with. It's not always true for all elements, but it's generally the case for the main group elements that we will deal with. Another really important, maybe a more important point though, is that the noble gas configurations, right? Neon, argon, krypton, xenon, etc. All of those noble gases have 8 electrons in the valence shell. And as we know, noble gases are very stable. They don't react with anything. Now, that's something interesting. And also, we notice that the most stable ions, like nitride or phosphide or oxide, those ions, the most stable ones, have noble gas configurations as well. So there's something to this noble gas configuration. And I want you to note that the noble gases all have 8 valence electrons. So it turns out that's going to be something very important, is that this 8 electron configuration in the valence shell has a special place in chemistry. Special stability is given by it. And you might want to ask yourself the question, why? Why are noble gases with this 8 electronic configuration particularly stable? Which I mentioned actually previously on one of the pages. See if you can answer that question. And then why do things like nitrogen gain 3 electrons? Or why does oxygen gain 2 electrons to become like the nearest noble gas? What about that special configuration? What's up with this 8 electrons? Why does that have this privileged place in chemistry? So see if you can address that. I think you can probably answer that. Let me know if you have any questions. Thanks for watching, and I will see you soon. Take care. Bye.